call the CPU the brain of the computer. But unlike a human brain, it doesn't think or understand. It follows instructions precisely, relentlessly, and at incredible speed. Every click, every game, every video you watch is ultimately reduced to simple electrical decisions, happening billions of times per second. In this video, we are going to trace the DNA of computing itself. We will start with the most minimal educational computers ever designed and follow their evolution all the way to modern CPUs and massively parallel GPUs. By the end, you will see how today's powerful machines are built on surprisingly simple ideas. So, how does CPU works? At its foundation, a CPU is made from transistors, billions of microscopic switches that are either on or off. By combining transistors, engineers create logic gates, such as AND, or NOT. These gates operate on binary data, the familiar ones and zeros that form the language of computers. Every action inside the CPU is synchronized by a clock. This clock sends out a steady electrical pulse that keeps all parts of the processor working in step. The faster the clock speed, measured in gigahertz, the more instructions the CPU can coordinate every second. The work of the CPU follows a simple but powerful loop called the fetch, decode, execute cycle. First, the CPU fetches an instruction from memory. Next, the control unit decodes that instruction, determining what operation needs to occur. Finally, the instruction is executed, usually by the Arithmetic Logic Unit or ALU, which performs calculations like addition and subtraction. To keep things fast, CPUs rely on registers. These are tiny ultra-fast storage locations inside the processor itself. One of the most important is the accumulator, which temporarily stores the result of calculations before moving on to the next instructions. For the evolution of computers, early computers were massive, mechanical, and unreliable. The first processors used vacuum tubes, which were bulky and generated enormous heat. The invention of the transistor and later the integrated circuit changed everything. Suddenly, entire processors could fit into a single microchip or single chip, making computers smaller, faster, and more reliable. In the late 1970s and 1980s, the rise of the Intel 8086 or 8086 introduced the x86 or x86 architecture, which still dominates personal computers today. This marked the shift from 8-bit to 16-bit processing, dramatically increasing how much memory a computer could access and paving the way for more complex software. As computers become more powerful, They needed to run multiple programs at once. This led to hardware support for operating system and protected mode, which isolated programs from each other. If one application crashed, it would not bring down the entire system. A crucial step toward modern operating systems like Windows and Linux. The 32-bit era introduced major performance improvements such as pipelining and caching or caching. Pipelining allowed CPUs to overlap instructions, much like an assembly line, instead of completing one task before starting the next. Caches, small but extremely fast memory layers labeled L1, L2, and L3 were added to keep frequently used data close to the processor, avoiding slow trips to main memory. While CPUs focus on handling complex tasks one at a time, GPUs are built for parallelism. A CPU typically has a small number of very powerful cores, optimized for sequential logic and decision making. A GPU, on the other hand, contains thousands of simpler cores designed to perform the same operation across large amounts of data simultaneously. This design is perfect for graphics. Rendering a video game requires calculating the color of millions of pixels dozens of times per second. A CPU is like a master chef, carefully cooking one meal at a time, while a GPU is like a kitchen, filled with hundreds of assistants all performing the same task in parallel. Today, GPUs have expanded far beyond graphics. Artificial intelligence, machine learning, and scientific simulations rely heavily on GPUs because neural networks involve massive amounts of parallel mathematical operations. Exactly what GPUs are built to do the best. What is SAP1? Simple as possible one. It's an educational model of a computer with only 16 bytes of memory. As for the architecture, it uses an 8-bit bus to move data between models like the program counter in the RAM. The instruction set programming, LDA, stands for load accumulator. It takes data from memory and puts in a register. Add, ADD, adds a value from memory to whatever is in the accumulator. SUB or sub subtracts a value from the accumulator. Out or OUT sends the accumulator's result to the display LEDs. And lastly, HLT tells the computer to stop. For the program example, to solve pi plus 2, a programmer writes code in assembly. It is in LDA 9H, add AH, out, HLT, and then converts it into a binary machine code to be toggled into the computer's memory switches. We have gone from 5 simple instructions in SAP1 to billions of transistors and parallel GPU cores. As we reach the physical limits of how small transistors can get, the future lies in specialized chips, NPUs for AI, and quantum processors. The brain is only getting faster. Thank you.